Welcome back. I'm Muggsy, and today I'm going to explain how to draw the Lewis structures of covalent compounds. Before we talk about drawing the Lewis structures of covalent compounds, you should know how to draw the Lewis structure of an atom, of an ion, and you should know a little bit something about ionic bonding. So let's review that really quick. If, for example, I had a sodium atom and a chlorine atom, you should be able to look in the periodic table, see that sodium's in column 1 of the periodic table, so it has 1 valence electron. Boop, boop, boop. And we would draw it right there. Chlorine is a halogen. It's in column 17 of the periodic table, or 7A, so it has 7 valence electrons. And so I'll draw those 7 around it right now. And I'll leave the single electron facing that sodium because I imagine they're going to interact in some way. And you should be able to know that if these two elements were to come together, chlorine is very, very, very electronegative. It really wants to pull electrons because if it gains just 1 more electrons, right now it has 7 out of 8. If it got just 1 more, it would have a full 8 out of 8 and it would be happy. Likewise, this sodium is kind of the opposite of that. It has 1 out of 8 valence electrons. So if it gained another electron, it would still only have 2 out of 8. So it's not very electronegative. It doesn't really want to gain more electrons. It's kind of the opposite. It would like to give up its electron, because if sodium gives up its electron, it would go down to 0 of 8, which basically means it would go back to the previous orbital, which would now be full, and that sodium atom would be stable. Remember, elements are stable when they have a full octet or an outer orbital of electrons. So that's exactly what would happen. Sodium would give up its 1 electron to chlorine, and in doing so, that sodium now has 8 out of 8 valence electrons because it goes down to 0 out of 8, and so you would go back to the previous orbital, which is now full at 8 out of 8. And it's totally stable and happy, but in doing so it's gained a positive 1 charge, which we just draw as a positive sign. The chlorine has now gained that electron from sodium, so now it has 8 out of 8 valence electrons, and it also is totally happy and stable, but it has gained an electron. Electrons are negative, so it has a negative 1 charge, and because sodium's positive and chlorine's negative, they're attracted to each other because opposites attract, and they form a stable ionic bond. Okay. That should have all been review. What's going to change up now is what if, for example, instead of having a big beaker full of sodium atoms and chlorine atoms, what if in our container we only had chlorine atoms? What would happen then? In this scenario, we now just have 2 chlorine atoms. There's no sodium atoms anywhere to be found. And these 2 chlorine atoms are, alas, very unhappy, unstable. Of course, atoms don't have feelings. When I say unhappy, I just mean the octet rule isn't satisfied, so they're incredibly unstable. They'll bond with anything they can find to become stable. And you'll never really find chlorine in nature in this form all by itself because it's so unstable. So you'll find it bonded to other things, like in our previous example. If this chlorine were to find a sodium, they would bond together to form NaCl, sodium chloride, otherwise known as table salt, which is all over our planet. So a lot of elements exist in chemical compounds such as NaCl because they're very highly unstable all by themselves. Now imagine there's no sodium to be found. In this case, there's only another chlorine. And so let's look at these 2 chlorines. This one has 7 out of 8 valence electrons, and so it's very unstable, unhappy. Same thing with this one, 7 out of 8, unhappy. Now, I guess this chlorine could give an electron to that chlorine, but now this chlorine would have 8 and it would be happy, but this would have 6 and it would be even less stable than it is now. And so that wouldn't work. And also, this chlorine isn't going to give up electrons. Chlorine's highly electronegative. It wants to take electrons. So it wouldn't just give them up to another element. That's totally against what it would do under normal energetic conditions. So it's out of the question for a chlorine to give up an electron to another chlorine. It's also only something that a metal does with a nonmetal, and you'll notice chlorine's a nonmetal. So it's two nonmetals instead of a metal and a nonmetal like a normal ionic bond. So that being the case, is there anything these chlorines can do to become stable? Well, actually there is. So imagine I have a green marker and you have a blue marker. Is there any way we could both have two markers? Well, there is. What if we just shared? If I share my green marker with you and you share your blue marker with me, we both have access to two markers. Now we can't maybe use them at all times in all places, but if I want to use blue, I can. If I want to use green, I can. And if you want to use blue or green, you can. And it's exactly the same with these nonmetals. So chlorine and chlorine can share this single unpaired electron with each other. And now, if we call this pool of two electrons, we call that a bond, a single covalent bond. Now we can reevaluate how many electrons each of these chlorines have access to. This chlorine has 1, 2, 3, 4, 5, 6, 7, 8, and it is totally stable. This chlorine, same thing, 2, 4, 6, and the bond counts as 2. There's 2 little electrons in it, 8 out of 8, and it's stable. When we draw a covalent bond, instead of having 2 single electrons that are circled, we just draw it as a line connecting those 2 chlorines. And that basically means the same thing. So this single line here basically equals 2 electrons that they're sharing. And as I said earlier, we call that a covalent bond. This is all one word, covalent, but I underlined it separately just to kind of explain the etymology of the word. Valent sounds like valence electrons because it means valence electrons. And co, in the beginning of a word, always means together. If you and I are the co-captains of something, that means we run it together. If we're codependent, it means we depend on each other. So covalent just means sharing electrons together amongst themselves. So that's a covalent bond. Specifically, we call that a single covalent bond, and yes, double and triple bonds exist, but you're not going to learn about those until a little bit later. Okay, let me give you a few more examples. You see here I've got the elements hydrogen and oxygen. Now, if hydrogen were a metal and oxygen were a nonmetal, these could form an ionic bond by hydrogen giving up its electron to oxygen, which would be great. Unfortunately, hydrogen is a nonmetal and oxygen is also a nonmetal. Hydrogen's kind of tricky in that it lives over with the metals in column 1, but it's in fact a nonmetal. It's a gas under normal circumstances. It meets all the criteria of a nonmetal. It just lives with the metals because it has 1 valence electron. So hydrogen can't give up its electron to oxygen, but they can share. So if we have each of these elements share, then this hydrogen now has access to how many electrons? If you said 2, that's correct. Remember, these 2 electrons are being shared, and so we draw a line to represent those 2 electrons. That means hydrogen has access to those 2, but so does oxygen. So that counts as 2 electrons for both of them. Now, how many total electrons can hydrogen have? Well, hydrogen and helium are the 2 smallest elements, and they only have access to the 1s orbital, which only contains 2 electrons. So hydrogen's valence shell is actually full. Hydrogen and helium are kind of an exception in that they fill up with only 2 valence electrons. All the other ones that we talk about generally need 8. That's the octet rule. Okay. So hydrogen's totally stable now. Let's look at our oxygen. It has access to 2, 4, 5, 6, 7. 7 out of 8 valence electrons. So oxygen is still unhappy. It started with 6 out of 8. Now it has 7 out of 8. Still not there. Let's give it 1 more hydrogen. Imagine if we have all these oxygens and hydrogens in a big container. There's other hydrogens floating around. So let's add another hydrogen here. This hydrogen has 1 out of 8 valence electrons, and so it's unstable. But if the oxygen and the hydrogen each share with each other, We draw that as a covalent bond. And now this hydrogen, just like this other hydrogen, has access to 2 out of 8, and it's happy. That's kind of a creepy looking face, but there we go. Likewise, this oxygen has 2, 4, and then each bond counts as 2, 6, 8 out of 8 valence electrons, and it also is now totally stable. And so we've formed, through covalent bonding, the very common covalent molecule, H2O, water. So water is a covalent compound, not an ionic compound, because hydrogen and oxygen are both nonmetals. Covalent compounds are made of nonmetals bonding with other nonmetals through these covalent bonds. Ionic compounds are made from metals and nonmetals coming together to form ionic bonds. Okay, let's do another example. Okay, imagine I have a phosphorus atom and a chlorine atom. And these are in a big container with all the phosphorus and chlorines I would ever need. And so we could use as many phosphoruses and as many chlorines as we need to make a stable compound. Now, phosphorus is a nonmetal, chlorine's a nonmetal, so this is going to be a covalent bond. Let's do their valence electrons right now. Phosphorus is in column 15, so we're going to give it 1, 2, 3, 4, 5 valence electrons. Chlorine's a halogen, so it has 7. Okay, right away we can kind of see that chlorine's going to want to form a bond with phosphorus in order to become stable. And when it does, this chlorine now has 2, 4, 6, 8 valence electrons, and it's fully stable. Our phosphorus, however, only has 1, 2, 3, 4, plus 2 from the single bond here to get 6 out of 8, and it's unstable. Okay, but remember, we have all the chlorines we need to make this a stable molecule, so let's just add on another one. 7 valence electrons, 7 out of 8, unstable. Let's form a single bond here. If they each share an electron here, this chlorine now has 2, 4, 6, and the bond counts as 2, 8 out of 8 valence electrons, and it's totally stable. The phosphorus now has 2, 4, 5, 6, 7 out of 8. So no longer 6 out of 8, but we're still not quite stable yet. We're going to need one more chlorine. So let's put it up here. And I kind of know the chlorine is going to interact with this phosphorus, so I'll put its single unpaired electron on the bottom. 7 out of 8, it forms a bond. It now has 8 out of 8 valence electrons and is totally happy. The phosphorus now has 2 unpaired electrons, followed by 3 bonds. Each bond is 2, so 2, 4, 6, and 8. Phosphorus now has 8 out of 8 valence electrons. It's totally stable. Generally, when we write the chemical formula for something like this, we would do the element to the left on the periodic table goes first. That would be the P. In this case, that's also the central element in the middle. So we would call this PCl, and then we've got 3 chlorines, so PCl3, and we would name this phosphorus trichloride, although you'll learn about naming covalent compounds later on. I'm just going to do 3 more examples, rapid fire in a row, and then I think you'll have seen lots of examples of how to draw the Lewis structure of covalent compounds through these single bonds. Let's start with H and F. H is in column 1. It's got 1 valence electron. Fluorine's a halogen. It's got 7 valence electrons. If they share, this H has 2 out of 2. This fluorine has 8 out of 8. We're good. We would call this chemical compound HF or hydrofluoric acid. That's kind of a special name. You'll learn about those much later. Okay, next one, potassium and oxygen. Potassium has 1, oxygen has 6. Surely there's going to be a single bond here. Actually, trick question. That single bond would never happen. Can you think of why? The reason is potassium is a metal. It's not a nonmetal. And remember, covalent bonding happens between 2 or more nonmetals. When there's a metal, potassium, and a nonmetal, oxygen, we're not going to do a covalent bond between them, we're going to do an ionic bond. So what would actually happen is this K would give up its oxygen, give up its valence electron to that oxygen, it would gain a positive charge, oxygen would gain a negative charge. We would add one more K, it would give up its valence electron to that oxygen. In doing so, it would gain a positive charge, the oxygen would gain a 2- charge. And then finally, we'd have a balanced stable ionic compound. We would call this K2O. The metal goes first, or the cation goes first, followed by the anion, oxygen. And we would call this potassium oxide. So this one was a trick question, ionic. Remember, 2 or more nonmetals, covalent. A metal and a nonmetal, that's ionic. Okay, sulfur and chlorine, last one. Sulfur has 6 valence electrons, 1, 2, 3, 4, 5, 6. Chlorine has 7, again, it's a halogen. If they each share one here, we draw that as a bond. This chlorine now has access to 8 out of 8 valence electrons, so it's totally stable. But this sulfur now has 2, 4, 6, 7 out of 8. It's not stable. We're going to need one more chlorine. Let's form a single bond there. This chlorine has 8 out of 8. It's stable. This sulfur also has 2, 4, 6, 8, 8 out of 8. It's also stable. We've made a stable covalent compound using these single bonds, and we call this SCl2, or sulfur dichloride. Again, you'll learn about writing the names of these later. Okay, pretty easy. Keep practicing it. Remember, you can just use as many of these different nonmetals, chlorines, hydrogens, whatever you need to make the molecule work and be nice and stable. The simplest molecule is the one that matters. So you could probably make bigger, more complicated molecules if I used like 5 sulfurs and 12 chlorines here. But the idea here is to make the simplest molecule you can possible. So with hydrogen and fluorine, that's just 1 hydrogen and 1 fluorine. With sulfur and chlorine, that's just 1 sulfur and 2 chlorines. Okay, I wish you the best. Good luck with this. I'll see you next time.